So, let us see shortcomings of a real life situation. Impulse trains cannot be generated. In fact, even one Dirac impulse cannot be generated impulse trains cannot be generated, even one Dirac impulse cannot be generated. So, ideal sampling is not possible. Impulse train sampling is not feasible. That is the first problem we face. There is also a second problem, and that is an ideal low pass filter with transition bands of 0 width also cannot be practically implemented. Because it requires either an infinite amount of hardware or an infinite amount of computation. Hardware or an infinite computation. In software. So, two things make it impossible to really do ideal sampling and then ideal recovery using an ideal low pass filter. Both these things are a problem, and yet this theory was worth studying. What we did was not a waste of time, because it was so informative and it gave us a picture between the discrete time world and the continuous time world. So, let us now address the possible imperfections, the possible real world imperfections that will have an impact upon our theory of sampling and signal reconstruction. We already know in any case that the sampling theorem that we have just discovered must be respected, but apart from heeding the sampling theorem, there are other issues that complicate the picture. One of them is, as I said, the non-existence or the impossibility of constructing an impulse train. What we can at best construct is a pulse train, say a train of rectangular pulses of non-zero width unlike the impulse train which has each pulse of 0 width and finite height. So, let us say we construct a pulse train instead of an impulse train. Pulse train instead of an impulse train. For this, let us first define the standard rectangular pulse. I will denote this by R subscript T of T and sketch it over here. This is time. It has a height of unity and a width on either side of t. So, this is from minus t to t and it has a height of 1. This is RT of t. This is RT of t. So, if you have RT of t, then we will define a rectangular pulse train as a uniformly spaced sequence of RT of t, and this will be of the form summation RT of t minus n Ts. So, they are placed at a distance of the sampling time from each other. This is over all n. So, this is a rectangular pulse train. Now, we can use the rectangular pulse train to sample the sequence instead of the rectangular the ideal impulse train. So, if suppose we use this, let us understand what happens to the result of sampling. Even before we do this, let us consider another example of sampling. Now, okay, suppose we do this over here. Suppose we carry out rectangular pulse train sampling, then let us see what we get. We can get two kinds of signals. I am going to make a sketch now of this is t, and let us say x t is this. Let us say x t is this. You have first of all a train of rectangular pulses, which we shall sketch over here. So, this is a train of rectangular pulses, basically this expression that we have over here, that is the train of rectangular pulses. Now, there are two different ways in which one can construct using rectangular pulses rather than ideal impulses, a rectangular pulse train instead of an ideal impulse train, the sample train. In one case, the samples will consist of rectangular pulses of height given by the value of x t at the point of occurrence of the center of the impulse, and the top of the pulse will be flat. So, if you have tops of the pulses which are flat and heights of the pulses given by x at n t s, then you have what is called, what I call, flat top sampling. we have what we call flat top sampling. Now, what is flat top sampling? Let us make a sketch, a separate sketch for this. This is xt in black, and flat top sampling will find samples of appropriate heights at each place. So, let me just do flat top sampling over here in green. So, you have this is the flat top sample train, which I will denote by x f of t. Now, what is the expression for x f of t? Mathematically, how does it represent x t? Now, we will say that x f of t equals x t at certain places. It is equal to, in fact, it is not equal to x t, it is equal to x of n t s, x f of t equals x of n t s over a width of time that goes from n t s minus t to n t s plus capital T, fine. So, is equal to this when mod t minus n t s is less than equal to t. T is half the pulse width. Remember, t is given according to this, equals 0 when elsewhere. So, this is what defines x f of t. This expression is very nice to look at, but it does not really tell us what is the sequence of mathematical operations that will give us x f of t. That is what we shall explore next. X f of t is a sequence of flat topped samples. Now, the best way to generate a sequence of flat topped samples where the height of each sample is determined by the local value of x t at the point n t s is as follows. We first generate x s of t, that is the original ideal sample train. So, first step, generate x s of t equal to summation over all n x n t s delta t minus n t s. First generate this. Now, having generated this, x s of t will be convolved by r t of t. That is to say that x f of t is nothing but the convolution of x s of t with with r t of t. if you want to understand this graphically, we just do this. We first carry out an ideal sampling. Let us do that. The ideal samples are these. We have these ideal samples. So, this sample train is nothing but x s of t, which has been drawn in gray. This is x s of t. Now, when x s of t is convolved with r t of t, where r t of t is, as we know, merely r t of t is just this. This is t and this is minus t and this is r t of t of unit height. So, when I convolve r t of t with x s of t, at each place where there is a sample impulse, it will be replaced by a rectangular pulse of height proportional to the sample impulse, in fact equal to the height of the sample impulse, and these will replace this everywhere. So, you will finally get this. Where the last one, the last colored function that we have here is, this is x of t, sorry. In black you have x of t, and in this color you have x f of t is in purple. So, you have x of t in black, x s of t in gray and x f of t in purple. This is the sequence of operations. First, do ideal sampling, that is calculate dt times xt, and on the result of this, with the result of this you convolve RT of t. With all this information in hand, let us try to understand what is x f of omega. X f of omega will be, by our knowledge of the convolution property, x s of omega multiplied by r t of omega. Now, we have solved some examples earlier of what r t omega would be. This was done when we were discussing examples of the continuous time Fourier transform. R t of omega is given by 2 sin omega t by omega. Fine. Now, let us examine this function 2 sin omega t by omega. Let us just plot this first. It will have zeros at certain points. At certain points where omega t equals k pi, that is at t at omega equal to k pi by t, k times pi by t. So, if this is pi by t, 2 pi minus pi by t minus 2 pi by t, then it will have zeros at these places, and otherwise it will have the general shape of a sinc function. So, let us plot it. So, this is the shape of RT of omega. Now, remember that pi by t is as large as t is small. Suppose t equals 4 times Ts. If t equals 4 times Ts, then pi by t will be correspondingly that much larger. Sorry, not t is 4 times Ts, Ts is 4 times t. Suppose Ts is 4 times t. That means the first minimum will occur at pi by t, which is pi by Ts by 4, that is pi 4 pi by Ts, a considerably far off point. In short, let us now make a spectrum of both the x s of omega as well as R t of omega together, because we have to multiply the two to finally get x f of omega. So, suppose x s of omega looks like this. X s of omega, let us say, is like this. This, let us say, is x s of omega. Now, as we know, R t of omega is going to be resembling this with t considerably larger than T s. So, considerably smaller than T s. So, we get a copy of this that looks like this. This is what we get, and when you multiply these two, you will end up with a product that perhaps looks like this. This is x f of omega in orange. So, you have now x f of omega, and you can clearly see that the fact that R t of omega is not flat in the vicinity of omega equal to 0, more particularly over the interval minus b to b, ensures that x f of omega is not faithful to x s of omega in the interval minus b to b. That is to say, because R t of omega is not equal to a constant in the interval mod omega less than b, or at least if we have been more generous, we will say mod omega less than omega s by 2, x f of omega is not equal to xs of omega over the interval mod omega less than b. Yeah, that's all that matters. Hence, even an ideal low pass filter with a specification of L omega equal to Ts for mod omega less than b equal to 0 for mod omega greater than b would not recover x omega without distortion. Fine, because as you can see from the diagram we just drew, xf of omega is irreparably mutilated by the non-flat nature of RT of omega. Let's write that over here, that this is RT of omega. This curve is RT of omega. This is xf of omega, and this thing in black of course is xs of omega. Thus, flat top sampling falls flat is not particularly convenient to use because it causes distortion. But let us just see how to minimize distortion in flat top sampling. Going back to the diagram we find that the zero crossings of RT omega occur at pi by t. Now, the farther away these zero crossings are, the more flat will RT of omega be in the interval mod omega less than b. The larger the zero crossings, of RT of omega, the more flat RT of omega will be over mod omega less than b, which is the bandwidth of the original signal. Hence, flat top sampling becomes more accurate small values of t in RT of t, which is simply saying which simply means that the rectangular pulse RT of t must resemble delta t more closely. So, this is, while this is difficult, this is at least reassuring, because it tells us that when flat top sampling is carried out with very narrow rectangular pulses, then inevitably the recovered signal using an ideal low pass filter will be pretty close to the original signal. So, we know how RT of t must be improved in order to make flat top sampling improve in performance.